Alright, so in this video I'm gonna be explaining another important paper with the title Message Passing Graph Kernels. This paper in 2018. Graph kernels have recently emerged as a promising approach for tackling the graph similarity and learning tasks at the same time. So in this paper, we propose a general framework for designing graph kernels. The proposed framework capitalizes on well-known message passing scheme on graphs. The kernels derived from the framework consist of two components. The first component is a kernel between vertices, while the second component is a kernel between graphs. The main idea behind the proposed framework is that the representation of vertices are implicitly updated using an iterative procedure. Then these representations serve as the building blocks of a kernel that compares pairs of graphs. We derive 4 instances of the proposed framework, and we show through extensive experiments that these instances are competitive with the state-of-the-art methods in various tasks. So a function acting on sets is permutation invariant to the order of objects in the set. If for any permutation pi, we can have this relationship. So this update strategy, this is aggregation. Here we aggregate and here we update. This update strategy illustrates the major weakness of such neural network. Taking the sum of messages sent from each neighbor is clearly permutation invariant. So it means that aggregation is good, because if, for example, if it is sum aggregation, the aggregation is very simple as a sum, a summation, then it's permutation invariant. But the problem is the update. So this is the motivation of this paper. So due to its simplistic nature, this function poses a serious limitation that restricts the representation power of message passing neural networks. So here, the proposed framework computes iteratively a kernel. So this kernel between each pair of the vertices, and t here is just time step. So when we update your time step, your kernel is now different. So the kernel values updates in this recurrence manner. The first term is kernel between two vertices, and now kernel between two neighborhoods. And here they propose this R convolution kernel. And then following this assignment kernel. Because we have two sets of vertices, V1 and V2, so we can't define a kernel between them using this equation. How similar the two vertices, two sets are. And then you can use it in equation 2. The update in equation 2 now becomes like this. So to compare a pair of graphs as a pair of vertices, now we can compute pair of graphs based on pair of vertices kernel. So we can compute kernel between two. But this is interesting. We use the same permutation invariant kernel functions. For example, you have two assemblies of neurons, G1 and G2. You want to know how similar they are. And for each V in V1 and each V in V2, if the pairwise kernel can be computed, so the kernel between the two graphs can be computed easily. And it is permutation invariant. As you see, if I change the order of the vertices, still you should do for all the pairs. So that's a good idea. And also they talk about link to WBL test, subtree kernel, and low rank approximation. And these are the experimental results. They did it for graph classification. Yeah, so these popular data sets, NCI1, enzyme, MUTAG. So they compare, for example, WL with this approach. There are different versions of their approach, and you see there are some improvements on the classification accuracy. Also, they compare with the proposed message passing graph kernel on QM9 dataset.